In this video, we are going to be looking at what sound is and how sound relates to what we already know about waves. So, sound just is a wave. It's specifically a compression wave traveling through matter. So if you remember a compression wave, like as it would look on a slinky, there'd be places where the coil is really close together and places where the coils are really far apart. And so when sound is traveling through air or water or stone or whatever it is, parts of that material will be compressed together and parts will be drawn out as it's traveling through. A lot of times we model sound as a transverse wave because it's a little bit easier to see what's happening with the transverse wave, but sound is a compression wave that goes through the material. One of the characteristics of sound, and one that you maybe have heard of before, is talking about the speed of sound. And what the speed of sound is will depend on the material. So remember, the only thing that changes how fast a wave can move is the material that it's traveling through. So generally, the faster sound waves will be in higher density substances. And also when substances are warmer, the sound travels faster through that too. So there is a small but measurable difference, say, in the speed of sound going through warm air versus cold air. So if we look at some examples of the speed of sound, in air, the speed of sound is 332 meters per second. That speed is what's referred to as Mach 1, and then Mach 2 would be double that and so on. That is the speed of sound in air at 0 degrees Celsius. At room temperature, it's closer to like 340. So again, it goes up a little bit with increasing temperature. You can see that it moves faster in water, faster yet in wood, faster than yet in iron, and faster yet in stone. Okay? The speed of sound in stone would be the speed of a P wave. So thinking back to what we know with earthquake waves from your 8th grade year. So P waves were the compression waves that moved through the earth when there was an earthquake. And so you can really think of a P wave as just being a sound wave, but a sound wave specific to stone. So we can use knowing the speed of sound, we can work out some problems. So if lightning strikes and you hear it 3 seconds later, how far away was the strike? I think it's a very common misconception. I know it's one that I held, that you count for every 1 second you count, the lightning is 1 mile away. And we'll see here with this calculation that's just not true. So we know a time, okay? We know a speed or a velocity of sound, that it's 300, and I gotta remember what the specific value was I gave you, 332, and we're looking for a distance. And if you remember way back to when we were doing motion calculations, we've got distance equals speed times time. So we've got distance equals 332 meters per second times 3 seconds. And so we find that that is 996 meters, or about 1 kilometer. Okay, so 3 seconds is 1 kilometer, and 1 kilometer is still less than a mile. It's 5 seconds is a mile. So if you were operating under the thought that every second was a mile, you're actually off by a factor of 5. Okay, so 5 seconds would be about a mile. So the question is, so you maybe have heard this: in space, nobody can hear you scream. Is that true or not? Can sound travel in space? And the answer is no. Sound cannot travel in space. Sound is a compression wave through matter. Sound is a mechanical wave that needs matter to travel. And so the sound cannot travel through space. There's not matter for it to travel through, because space is a vacuum. Looking at how we're able to hear sound. Now this is something that I'm not probably going to test you on, but I just want you to understand like how you're able to hear sound. So basically, your outer ear, the reason why it has its goofy shape is so that it can collect sound. That compression wave can focus the compression waves down into your ear canal. Then the sound waves travel down through the ear canal and they cause the drum to vibrate. This sends waves through the liquid into the inner ear. And then there's hairs on inside this cochlea here, and those hairs, so basically you have little hairs there, and as the compression wave moves through them, the hairs move to one side or the other, and the nerves the hairs are attached to pick up that motion and send that electrical signal then to your brain, and then your brain interprets it as the sound that you're hearing. So if you think about it, like, you know, if there's no one around to hear a tree falling in the woods, does it make a sound? It's certainly going to make a compression wave, but if you think of the sound as like the human interpretation of it, then the answer would be no, or, you know, or is it a squirrel that hears it or whatever. But so again, it depends on what you call sound. Is it sound when the brain interprets it, or is it sound when you have the compression waves? So the way we experience sound, okay, so you can think about like different wave properties that there are, and one wave property that other waves have was frequency. And so frequency of a sound is related to what pitch the sound is at. So pitch means, are you talking about a low sound, or are you talking about a high sound? Okay, so the higher the pitch, the higher the frequency. I expect you to know that humans can hear frequencies anywhere in the range from 20 to 20,000 hertz. Anything above that range of 20,000 hertz is considered to be ultrasound. And so when someone's getting ultrasound of something inside their body, they're just using some sort of sound above 20,000 hertz. So it's a sound that we can't hear. It's probably well above 20,000 hertz. I guess I've never looked into specifically what it is. And anything below that range is considered infrasound. Okay? So like there can be sounds, there might be sounds all the time, but if they're below 20 hertz, you're not going to be able to hear them. The other part of our experience of sound is we can experience the loudness of sound. Okay? So the loudness of sound is going to depend on the amplitude of the sound wave, so how big the disturbance is, how big the pressure variation is between low pressure and high pressure. That's going to give us the amplitude of the sounds. And we measure loudness with using the decibel scale, basically because there's such a big range of loudnesses that humans can hear. We can't use a linear scale to capture all that because we'd be talking about too many different big numbers. And so whenever that happens, we use a decibel scale. And this is just like the Richter scale for earthquakes too, is also a logarithmic scale. So every time you go up 10 decibels, the amplitude of the wave is 10 times bigger. So let's say if I drew a wave here, if this, let's just pick a number, was registered as 60 decibels, then to make it 70 decibels, I'd have to go 10 times bigger. So I don't know if that's quite 10 times bigger or not, but we'll say it is. And if I wanted to do something that was 80 decibels, I would have to go 10 times bigger than that. So again, I don't think this is actually 10 times bigger, but we'll pretend it is. And if I wanted to go 90 decibels, I'd have to go 10 times bigger than that, so I wouldn't be able to fit that on the screen here. Okay? And if I wanted to go to 50 decibels, I'd have to make it 10 times smaller, so we'll pretend like. Okay? So there's a huge range in amplitudes as you go from 50 to 60 to 70 to 80 decibels. Okay? So I'm going to get rid of these lines I drew all over the place here. Okay? So when we look at decibels, some familiar things, okay? So some ones that I want you to know, if we look at a conversation in a quiet living room, so hopefully you can read these. This is at 60 decibels, so that's one that I want you to know. Okay. A soft whisper would be considered 40 decibels. The quietest thing that you can hear is at 0 decibels, so decibels can go negative. If the sound is quieter than what you can hear, then it would have a rating below 0 decibels. Okay. Loud music in a discotheque, because we all go to discotheques all the time, are at 100 decibels. A ship's engine room is 120. I think a plane taking off, it's one that wasn't on here, but I've seen a lot, is 130. And up here is when it starts. Anything above 100 is where you can start getting damage to your ears. And how quickly that damage happens depends on how long or how many decibels it is. Whether, like, if it's 130 decibels, you can have instant damage. At 100 decibels, you can have slow damage. Okay, so something to consider when you're deciding how loud to listen to your music is you can get hearing loss from it. Okay. All right, so some questions just to check our understanding. Sound A has a frequency of 400 hertz and sound B has a frequency of 800 hertz. Which sound will sound higher? It's sound B. With the higher frequency, we'll give it a higher pitch. Sound A has a frequency of 400 hertz and sound B has a frequency of 800 hertz. Which sound will sound louder? You can't tell because it depends on the amplitude, which I didn't mention. Now the higher one might sound louder to you if that just happens to be you're more sensitive to that, but it's not. But that, again, that might depend on the individual, because some people, like older people, lose their high frequency hearing first, and so something that might sound louder to you might sound quieter to them. Okay, so in some ways loudness is an individual experience type thing. How many decibels louder would 100 fireworks be compared to 1 firework? So again, if you think of the way the decibel scale worked, since it's 100 times as intense, because you have 100 times the number of fireworks, 100 is 10 times 10 for intensity, which means it's 10 decibels plus 10 decibels, because when you multiply the regular intensity, you add the decibel numbers. So you would be 20 decibels louder. Sound A is 30 decibels louder than sound B. How many times louder does it sound? Okay, so if you have to go to get your decibels, if you're going 10 plus 10 plus 10 for decibels, then for loudness, the way we experience it, it actually will not sound like 1,000 times louder. It's 2 times 2 times 2 for loudness. And so 2 times 2 times 2 is 8. Okay, another thing that sound can do is sound when you have something that's moving relative to you. So if you have a source of a sound that's moving relative to the receiver of the sound, you get what's called the Doppler effect. So we're all probably familiar with the Doppler effect as like a train goes by or a police car goes by, and you hear that change in the pitch of the siren. Or if you're a NASCAR fan and you look at when the cars go racing by and you get that whole meow, okay, that's because the sound waves can only move so fast. So if you're moving in the direction the sound waves are traveling, the sound waves get piled up closer together, leading to a smaller wavelength and a higher frequency. And behind the vehicle, the sound waves get drawn out, leading to a longer wavelength and a lower frequency. The faster the object is moving, the greater the Doppler effect will be. We want you to know about musical sound. Okay, so that's one of the more interesting things about sound, is what makes a sound musical. Okay, so for a musical scale, so the familiar musical scale that we're used to, the do, re, mi, fa, sol, la, ti, do, That's a series of sounds that has frequencies with some sort of mathematical relationship. So our musical scale, the one that we use, has actually 12 notes, depending if you're looking at all the half steps, with the frequency doubling over each octave. So if you compare the do to do, there's going to be a doubling in frequency there every time I go up an octave. When you have notes that sound good together or they harmonize with each other, that means that they have frequencies that are related by low whole number ratios, and we'll see that on the next page. When notes are dissonant or sound bad together, that means that they have notes, they have high number ratios. Okay? And then the other thing is different instruments will sound differently because of the shape of the waves is different. Okay? So looking at that, a tuning fork has one pure tone to it, and its wave is simple. A flute still has a fairly simple wave pattern. Now this tuning fork and this flute are playing the exact same note. Every time we have this trough here, if you look down, it is lining up with a crest of the flute. Okay? Or one of the crests of the flute. So they're playing the exact same note. It's being repeated in the same interval. Okay? So again, they're playing the same note. They have a different sound quality because what makes up that repetition is different. Looking at the musical scale then, okay, so here is one example musical scale where we have going from middle C to C, all right? And the way they're related is over to the side. So middle C with itself obviously has a 1-to-1 ratio. And as I've already mentioned, when you go to the higher C, it's a 2-to-1 ratio, okay, because you double as you go up the octave. Now when you go through the other ones, there's all sorts of different ratios. When I mentioned harmonizing, so like for example, what makes up a major C chord is the C, E, G, and then the next C up. So if you look at how they're related to each other, we've got 1-to-1, 5-to-4, okay, 3-to-2, and then 2-to-1. Those frequencies are all related to each other by small whole numbers, and so they sound good together. If I was to play, let's say, the middle C with the B, so it's a 15-to-8 ratio, that wouldn't sound so good, okay, or at least wouldn't sound as good as other ones. If I have like something that's out of tune, it's going to sound even worse because they're going to be really large whole number ratios. So what causes instruments to sound at the frequency they do depends on what sort of standing wave will resonate on that instrument. So we've already learned about standing waves. So waves add with themselves, so you get a series of nodes and antinodes. Okay. So if you think about like for example, a flute is essentially like an open pipe. It's open at each end. So the end where you blow into it, and then the other end where the other end of the tube, or actually wherever your fingers last, is depressed. Okay, so flute is called an open pipe, and the standing wave that will sound the loudest on a flute is one that has an antinode at either end, and then a node in the middle. And so if we look at this wave here is half of a wave. The standing wave that's on the flute is 1/2 of the wave. And so for an open pipe, the length of the pipe is equal to 1/2 the wavelength of the wave. Now flutes have more than one harmonic, so you can also get any standing wave where you have antinodes on either side. Okay, and so that's what gives a flute its characteristic sound, is what pattern of standing waves can you have. Whoops. If you think about like when you blow into a pop bottle is open at one end and closed at the other. So here we want a node at the closed end and an antinode at the open end. And so for here, the length of the pipe is equal to 1/4 of the wavelength. Okay? And so the relationship for the waves of so when you blow into a pipe that's closed at one end and a pipe that's open at one end are going to be different from each other. For a guitar string, the guitar string will be held down at either end, and so there will be nodes at either end of the guitar string, and there will be an anti-node in the middle of the guitar string, so the length of a guitar string is equal to 1/2 of the wavelength of the first wave that fits onto it. Okay, so these relationships for an open pipe, a closed pipe, and a string are all ones that I want you to know. So doing an example there, if a flute is playing an A at 440 hertz, what is the length of the flute? So we go back, and a flute is an open pipe. Okay, so since it's an open pipe, you go back to look at an open pipe, and the length is equal to 1/2 the wavelength of the flute. So if I could figure out, and that's ultimately what I want, is I want to know what is the length. Okay, we were given a frequency. Well, we know from before with doing wave calculations that frequency can be related to wavelength, but we don't know that. But we have the equation velocity equals frequency times wavelength. So when I blow into a flute, I'm putting a wave through the air inside the flute. So I know the velocity is 332 meters per second. Okay? The frequency I was told was 440 hertz. And the wavelength I need to find out. So now that I have that relationship set up, I can solve for wavelength. I can take 332 and divide by 440. And so I get the wavelength equals 0.75 meters. So then the length would equal 1/2 of 0.75 meters. So the length of the flute would equal 0.38 meters. And if you're a flautist, you can get out your flute and you can figure out where you finger it to hold an A and see whether or not that's actually 0.38 meters long. All right, so that's all there is for this video.